started discussing optomechanics, and in particular we discussed how to measure the displacement of a mechanical oscillator using the light field. And I already mentioned the fact that if you try to measure the displacement, for example, by looking at the phase shift of a laser beam that is back reflected from the optical cavity, then the phase shift can be proportional to the displacement, and so you would be able to read out the displacement. And then we started by looking at the displacement of a single harmonic oscillator in thermal equilibrium, and I briefly discussed that in thermal equilibrium you would expect the harmonic oscillator to oscillate at its eigenfrequency, but to have an amplitude and also a phase that is slowly varying, and it will change on a time scale that is given by the damping time. So that is true in thermal equilibrium for a single harmonic oscillator. I also mentioned already that if you look at the motion of the mirror, then of course it will be influenced not only by the single fundamental mechanical mode, but there will be many other mechanical modes, such as this one and the higher order mechanical modes. So in truth, the position of the mirror will be a superposition of all the normal modes, of all the normal mode coordinates in the mechanical system. And therefore, what you observe will look much more complicated than this. And it is pretty clear that the best thing to deal with this is just to do a Fourier decomposition, because then you can separate the different frequencies of the different normal modes. And so that brings us to looking at the Fourier spectrum of the motion. And the essential point about the Fourier spectrum is, of course, that this is not a perfectly periodic motion. It slowly fluctuates in amplitude and phase. And so if you take the Fourier spectrum of a single run, you will also get a rather fluctuating spectrum. And so you have to average over many runs, and it is this average spectrum, the average Fourier spectrum, that we want to discuss now. And it will turn out that the average Fourier spectrum has a direct connection to the Fourier transform of the correlator of the potential fluctuations in thermal equilibrium. And that then will also lead us to a connection to the fluctuation dissipation theory that tells you that the noise at a particular frequency is particularly strong if the system has a strong response to external perturbations at that frequency. So this is what we want to discuss today. And I want to keep it relatively general because it applies to all kinds of systems in thermal equilibrium. Okay, so this is a brief theory section because it's sufficiently general, and we will deal with the fluctuation spectrum and the relation to the fluctuation dissipation theory. So what is the situation we want to consider? Let's take a trace like this one for a single harmonic oscillator again, and take the observation over some limited time, let's call it tau. And now we simply want to take the Fourier transform of this. So I want to call this x tilde of omega. And now the question is how to define the Fourier transform. I want to integrate from 0 to tau. E to the I omega t times x of t, where x of t is just the single run that I display here. And now, with regard to the normalization, of course, you know there are different choices for normalizing a Fourier transform, and it will turn out to be very convenient if I enter 1 over square root of tau in front. So let's try to plot the result that you would observe in a single run of the experiment. X tilde of omega, just like any usual Fourier transform, will be complex valued. I want to plot some real quantity, and the quantity to plot and also the quantity to average later will be rather the magnitude squared of X tilde. We will discuss the units in a moment, but the point is that since x of t is not really a periodic function, it's a rather complicated function, fluctuating function, when you actually carry out the Fourier transform, you will see something rather complicated like this. It will be symmetric around omega equals 0, simply because x tilde of minus omega equals the complex conjugate of x tilde evaluated at omega. This is simply a consequence of x of t being real valued. So if you take the magnitude squared, you see something symmetric, but otherwise it is strongly fluctuating. However, you would observe that the peak or the bulk of the density really sits at the frequency of these harmonic oscillations. So this is not yet very useful. And so what you want to do is you want to average this over many experimental runs. So suppose you complete the same run once again. Again, you will see a trace similar to this one, but having a different fluctuating amplitude and phase. And you repeat the same again and again and again. Now, it would be stupid to average x tilde, because just as with averaging x of t, you just would obtain 0. But the squared of x tilde is a good quantity to average. So I just plot for now the result that you have to expect, and later we will discuss how this result comes about. So what happens if I average is that this forest of spikes really becomes smooth, and in this case for a harmonic oscillator, and this is something which we will discuss, it simply becomes a Lorentzian. And so the whole function is symmetric with respect to omega equals 0. So that is the average over many runs. So now this is the point to make a remark about the units. What are the units of x tilde? Well, you see, it's the units of x multiplied with a time divided by the square root of a time. So overall it's x times the square root of a time. So that means if I plot the squared x tilde, that is my spectrum, then I get x squared times something with the units of a time. But since this is a spectrum, in the end we want to integrate over all omega. And so it is much more convenient to say that instead of having to multiply with a time, I divide by a frequency, which of course is the same. In particular, this will mean if I integrate over all frequencies, I will get back an x squared, and we will see that in a moment. So this, in real physical units, will have units of meters squared per hertz. And that is a unit that you will find very often if you look into the experimental literature and look at these kind of spectra. Sometimes people choose to plot things such as to reveal the fluctuations in meters individually, And so you would take the square root of the spectrum again, and then you would have units of meter divided by square root of hertz. So that is a very strange unit when you first encounter it, but it does make sense. So it's just the square root of the spectrum. So I can just note this here. If you take the square root of the spectrum, then you have units of meter divided by square root of hertz. Okay, so now let's have a closer look at the average spectrum. Simply by taking the formula here, taking the square, and taking the average. And we will see that there's an interesting relation between the spectrum as defined here and the Fourier transform of the correlator. Okay, so the relation that I'm going to derive has a name, and it's called the Wiener-Kindchen theorem. But it's really quite simple. So, again, x tilde of omega has been equal to 1 over square root of tau integral e to the I omega t x of t. And now if I take the square of this and average, what happens? Well, if I take the square of this, instead of one integral, I will have two time integrals. Both of them between 0 and tau. And since I take the magnitude squared, once I have e to the I omega t1 and once I have e to the minus I omega t2. And then I have the product x of t1 multiplied by x of t2. And since I take the average, I can pull the average into the integral simply because only x of t is the fluctuating quantity. So now there is an important remark, namely, if we assume we are in some steady state, then no point in time is special. If no point in time is special, then this correlator will only depend on the time difference. Now this is very convenient because you see that also the prefactor, the phase factor, depends only on the time difference. So if it were not for the boundaries of the integral, then it would be automatically straightforward to change variables such that instead of integrating over t1 and t2, I integrate over sum and difference variables. And then only the integral over the difference variable is interesting and the integral over the sum variable is trivial. However, of course, I do have to respect the boundaries of the integral. And so now here comes some approximation that will become exact in the limit of large tau. And the plot I'm now going to make is the plot that you see again and again when people discuss these kinds of correlators. So the plot contains both T1 and T2, the T1, T2 plane, and I want to plot this correlator in the T1, T2 plane. So typically the behavior of such a correlator is such that if the 2 points in time are equal, well, I just get the variance of x, and this is some finite quantity, so that is what happens on the diagonal. I get some finite quantity on the diagonal. And now, if I change the difference of the time coordinates and move away from the diagonal, what happens is that the correlations of these fluctuations become less and less important. If I move away in time, then the correlations decay, simply because if these fluctuations are very far apart, taken at very different points in time, then they practically don't know anything about each other. Okay. So this is my fluctuating curve, and I take T1 here, I take T2 at some completely different, far removed time, then both the amplitude and the phases at this point will have nothing to do with the amplitude and phase at that point, and as a consequence, x of T1 will fluctuate completely independently from x of T2, and if both have average 0, then the correlator here just vanishes. So that is the typical behavior if I plot x of T1, x of T2 versus the difference in time coordinates. I just get some exponential, some decay, and in the simplest case, say would be exponential. And so if I move away from the diagonal, the correlator decays. So typically you can associate some time scale to this, some correlation time, and beyond this correlation time you can approximate the correlator by 0. So if I want to indicate the area, the region where the correlator is sufficiently different from 0, I would get a kind of band around the diagonal. So now the idea will be the following. I will allow myself to change to sum and difference variables. Now, typically the boundaries of these integrals would then look rather complicated, but in a second step I will allow myself to integrate over the difference in times from minus infinity to plus infinity, which in this picture simply means that I integrate along this line, not respecting the boundaries of the square. And I will be able to do this because you see that the integrand, the correlator, only is non-vanishing in a tiny region around the diagonal, so I can simply drop what happens in infinity. I will make a small mistake, especially here and here, but if the interval tau becomes large enough, then relatively speaking this mistake will be small. So that is the idea. And so what happens with this integral? One over tau is the prefactor, but now look, I want to integrate over the difference in times. Let's call this t. And then, in a second step, I would have to integrate over the sum of times from 0 to tau. But since there is no further dependence on the sum time, I can simply evaluate that integral and it gives me another factor of tau. Okay, so these cancel conveniently, and that is the reason why ultimately in the beginning I chose this definition. And what you arrive at is nothing but the Fourier transform of the correlation function. And so previously when we discussed noise spectra, we already gave a name to the Fourier transform of the correlation function, we had the two quantities that we correlate, and then omega as a subscript. So that is the Wiener-Kinchen theorem. What it tells you is that if you take the limit of tau tending to infinity, then the average of the Fourier transform squared of a particular realization of your noise process is equal to the Fourier transform of the correlator. And so that is very convenient because this noise spectrum is the one you measure in experiments, and that correlator is the quantity which you typically evaluate in theory. So for example, in electrical circuits, this is what a spectrum analyzer would directly give you, and that is what the theoretician would calculate. Okay. So now, let's come back to the question of looking at the area under this spectrum, under the spectral noise density. So what is d omega over 2 pi the spectrum? So you will see that the 2 pi is very convenient because now if I insert this definition, then the integral over omega can be put inside. And you see that the integral over omega, over all omega of e to the I omega t, obviously is 2 pi times the delta function in t. The 2 pi cancels, I conveniently get a delta function in t, and overall I get the average of the square of my noise process taken at t equals 0. But since I'm in steady state anyway, I have a stationary noise process, the time point does not really matter, and so I can simply write this as the average of x squared. So what we learn is that if I take this spectrum and take the area under the full curve, then apart from the factor of 2 pi, I will reproduce the variance of x. And we already discussed that for the harmonic oscillator and thermal equilibrium, the variance of x would directly give you a measure of the temperature. So that is why often in experimental papers you would find plots of this noise spectral density, and then they will talk about the area of it in order to extract the temperature. Okay. So this is a completely general property of a stationary noise process, this relation between the average of the square of the Fourier spectrum and the Fourier transform of the correlator. But now we want to be more specific. We want to look at systems in thermal equilibrium. And there is an interesting relation between the noise spectrum, or the Fourier transform of the correlator, and the susceptibility, that is the linear response. So this relation, which you might have learned in statistical physics, is called the fluctuation dissipation theorem. So I'm not going to derive it here, but I'm going to discuss it and discuss its consequences for our applications. What is the situation? Imagine you have an extremely complicated interacting many-body system, say many particles in a liquid that interact with each other. It will be very difficult in detail to describe their motion. But now let's say, pick one of the particles and try to apply a force to that particle. Some arbitrary time-dependent force. Then the position, say, of this particle, or the velocity of that particle, or any other observable that you could be interested in, will show some response to the force. So you can compare the situation when the force is present with the situation when the force is absent and see how, say, the coordinate changes in between these two situations. Now it is obvious that for such a complicated system, the detailed response of the particle will depend on its surroundings, on what the other particles do. So if you repeat the same experiment again, say with this particular particle in the same position, but all the other particles at different positions, the response will be different. So in order to talk about response in a meaningful way, you should average the response over many repeated runs. Average it over all the possible configurations of the other particles. Yeah, so delta x in average is the quantity to look at. And now if the force is weak enough, the response will be proportional to the force in some sense. Now in general, there's no reason to suspect that the response at one point in time only depends on the force at this particular point in time. Rather, in general, there will be memory effects, so you give a small kick to the particle and even some time later it will still feel the consequences of this kick. So you could write this down in terms of having an integral kernel here, or it's better even to do this in Fourier space. So that is the story about the susceptibility of the system. It may be very difficult to calculate in detail, and in each particular run it would depend on the configuration of all the other particles, but it is convenient, say, to define the average response. And at least you know that if the force is weak enough, you expect this average perturbation, the response of the system, to be linear in the applied force. Yeah? So much about the response of the system, and we will see later why the name contains not response but dissipation. Now this is one thing. And in particular you can ask, what happens if I have a sinusoidally varying force? What is the response of my system at different frequencies? Maybe there are frequencies at which it responds more easily. For example, in such a system, in a real liquid, you might have a strong response at roughly about 10 to the 12 or 10 to the 13 Hertz, which is the vibrational frequency when a single atom vibrates against its neighbors. Yeah? Now, let's instead look at something which at first sight looks very unrelated, namely fluctuations in thermal equilibrium. Do not apply any force, just look at the system as it moves in thermal equilibrium. All the atoms bump into each other, so it's a very complicated motion. Nevertheless, you could start looking, say, at the time evolution of this coordinate, and it will be a fluctuating quantity. And again, it would be reasonable to try to describe this statistically and say, look at the correlator of this fluctuating quantity. And so now it turns out that if you Fourier decompose this correlator in terms of the noise spectrum that we just discussed, you will find that the noise spectrum will be particularly strong. It will have peaks exactly at the same frequencies where the response is strong. Somehow qualitatively this makes sense, because if you imagine that this system were coupled to some external heat bath that provides a fluctuating force and thereby induces these thermal fluctuations, then it is clear that if the response of the system is strong at a particular frequency, also in particular the response to these thermal fluctuating forces will be strong, and so the thermal fluctuations will be strong. One can even expand the whole picture. One could say, let's look at a force applied to some other particle and the response of some coordinate of this particular particle. And again you will find that the response is tightly connected to the correlations of the coordinates of these two particles. Okay. So in general, the fluctuation dissipation theorem will tell you there is a relation between the noise and the susceptibility, that is the linear response. But this relation only holds in thermal equilibrium. So it's a very special property that simplifies things in thermal equilibrium. Now, in order to make it quantitative, I have to specify in more detail what is the susceptibility, that is the proportionality constant sitting in here. And so it's convenient to switch to Fourier space to decompose into frequencies, to look at the average response, the average perturbation induced by a force as a function of frequency, and say this is proportional to the Fourier decomposition of the force at this particular frequency, and the proportionality constant we will call a susceptibility. Often it has the name chi, and we will give it the subscript xx, and I'll explain this in a second. Okay. So this is the susceptibility. Now the first x, it relates to the response that you're looking at, delta x. You're measuring the response in the variable x. And the second x in this case relates to the force that is, so to speak, the direction into which you apply the force, or more precisely, the variable in the Hamiltonian to which the force would couple, because you would write minus x times f into the Hamiltonian if you couple a force to the x coordinate. So this defines the susceptibility. And now it's easy to write down the fluctuation dissipation theorem. So in the classical limit, it simply says that the noise spectrum at a particular frequency is proportional to the susceptibility at that frequency. But more precisely, since the noise spectrum is a real valued quantity, and the susceptibility in general will be a complex quantity, it is clear that the relation cannot look like this, and so you have, turns out, take the imaginary part of the susceptibility. And then what is the prefactor? Well, in the most simple physical systems, such as a harmonic oscillator, the susceptibility is completely independent of temperature. It depends on the spring constant, it depends on the damping rate, if you have a damped harmonic oscillator, it depends on the mass, but it does not depend on the temperature. The response is the same at all temperatures. Nevertheless, the fluctuations, they do depend on the temperature. And so it is very reasonable to expect that some of the temperature enters. And if you think of the fact that, according to the equipartition theorem, the variance of x goes linearly in temperature, it's not surprising that here the temperature enters linearly. And so the rest of the prefactor I simply have to introduce here without further explanation. That would be 2 times thermal energy divided by omega. So that is the fluctuation dissipation theorem in the classical case. Why is it called dissipation? Well, if you work out the meaning of the real and the imaginary part of the susceptibility, you will find that if you apply a force to a system and ask about the power that is dissipated in the system while applying the force, it is the imaginary part of the susceptibility that tells you this power that is dissipated. So that is the dissipation part, so to speak. And we will discuss this for the example of the harmonic oscillator. Now, since we are at it at the moment, we can just as well have a brief look at the quantum case. What do you expect for the quantum case? Well, somehow, first of all, h bar should enter. And secondly, you should be able to write down a formula that in the limit of high temperatures, temperatures much larger than h bar omega, reproduces the classical case. So that is the quantum formula. We can check this briefly. What happens if you really have high temperatures? Well, in that case, you would start saying that the exponent is small. H bar omega over kBt is small. So you expand it in a Taylor series, the one cancels, and what you're left with is just 2 times kBt divided by omega. So that simply reproduces the classical case. And then you can also ask what happens if I go to 0 temperature, if I go to the ground state of my system. Or in other words, if temperature is much smaller than h bar omega. Well, what happens then is that the exponent blows up, because temperature goes to 0. But for positive frequencies, this is fine. Then you have e to the minus infinity, which is 0, and you just are left with 2 times h bar. For negative frequencies, then the exponent overall will be positive. It will blow up. You get e to the plus infinity, and so this gives you 0. So in that case, the spectrum has a theta function, a step function at 0 frequency, and then 2 times h bar times the imaginary part. And that is characteristic of a noise spectrum at 0 frequency, because you will remember our little discussion when we first discussed noise spectra. I told you that if I take the noise spectrum of some system, then the positive frequencies describe the ability of the system to absorb some energy, and this ability is always there, in particular even at 0 frequency. An atom can absorb some energy even at 0 temperature, Whereas at negative frequencies, it signifies the ability of the system to emit some energy to other systems. And of course, there is no such ability at 0 temperature, simply because there are no thermal fluctuations left. And so it makes a lot of sense that at 0 temperature, you get this step function such that negative frequencies are completely suppressed. There is simply no energy left in the system. Okay. So this is the general fluctuation dissipation theorem, and it holds for arbitrarily complicated interacting nonlinear systems. But the point is that for our case, of course, it's simpler. We have the simple damped linear harmonic oscillator And so we can very simply evaluate the susceptibility and then quickly get the noise spectrum. And that I want to do at least once, just to introduce the general kinds of calculations that are done in this context. So let's apply this to the damped oscillator. Now, let's write down the equation of motion for the oscillator, which would include the acceleration term. Now, if I want to bring everything but the external forces to the left-hand side, I would have the restoring force, plus I would have the damping force. So that is proportional to the velocity, and it contains the damping rate. Now, this I have to set equal to any external forces. Which external forces are there? Well, even if I don't really apply an external force, then in thermal equilibrium, because the damping tells me that I'm connected to some thermal environment, I also have thermal fluctuations. Which again is some noise process, some noisy function of time. Plus then there is my external force to which I want to calculate the response. Now, as I told you, the idea in defining the susceptibility was to look at the average response, not the particular response in any particular run of the experiment, but the average response. So I want to average this equation, which is easy enough because it's a linear equation. And in averaging it, I get rid of the thermal fluctuations. And so all that remains is my systematic external force, which I always apply in the same manner. Now I can go into frequency space, which is more convenient for this linear equation. And so I will find that any time derivative will produce a minus I omega. And if I take the second derivative, I get minus m omega squared. Here I get plus m capital omega squared, the eigenfrequency. And here I get minus I m omega gamma. I do not want to write down delta x because x anyway has an equilibrium value of 0. So x equals delta x. Now if I compare with my definition of the susceptibility, I find that x should be susceptibility times the force, or in other words, what sits inside the brackets here must be the inverse of the susceptibility. That was simple enough. Of course, for a general interacting nonlinear system, it would hardly be possible to calculate the susceptibility analytically. Now, what we are really interested in is the imaginary part of the susceptibility. That is what enters the fluctuation dissipation theorem. Well, so I have to take the imaginary part of 1 over this expression in brackets, and that just means that I extract the imaginary part of this expression, bring that into the numerator, and take the square of the real part plus the square of the imaginary part in the denominator. So that is the imaginary part that I'm looking for. And so now if I look at my fluctuation dissipation theorem, I simply find that the noise spectrum would be 2 times thermal energy divided by omega times this expression. So since I divide by omega, I get rid of the omega in here. At this point I could remark that this expression tells you that the imaginary part of the susceptibility is antisymmetric in omega. If I reverse the sign of omega, I also reverse the sign of the imaginary part because of this omega up here. And this is a general structure, so the imaginary part of the susceptibility is antisymmetric with respect to frequency. So that's why it's a good thing that in the fluctuation dissipation theorem I divide by the frequency in order to make the noise spectrum symmetric in frequency, which it is. Okay. Well, so how does this look like? You see that provided gamma is small enough, this function will have peaks whenever the denominator is relatively small. And it will be small if this part becomes 0. And again, that will be true if omega, little omega, the frequency at which I evaluate the spectrum, equals capital omega, the resonance frequency. So that is the structure which we anticipated in plotting these Lorentzian functions. But if gamma is really small as compared to omega, then it's always a good idea to simplify this function around the resonance frequency, where it really becomes a Lorentzian, and this is what I want to do now. So I want to say, let's assume that gamma, the damping rate, is much smaller than the mechanical frequency. And that means simply that if you look at the free decay of this oscillator, then it will ring down for many periods. So that is what I want to assume, and then as a next step I just pick the region around the resonance frequency. So if that is true, I can simplify things. So first of all, capital omega squared minus little omega squared becomes capital omega plus little omega times the same with a minus sign. Now this is generally true, of course, but now if I'm near the resonance frequency, I can replace this by twice capital omega. I do not want to do any replacement here, because then of course I would approximate this by 0. I do have to keep this order. And then here again I would say, oh, this is approximately capital omega. So that's the kind of approximation I want to do now. Now this is already a Lorentzian. You see that it's a constant divided by the square of the difference in frequencies with respect to the resonance frequency plus some other constant. And the only task that remains is just to simplify this expression. So let me pull out kBt and some m omega squared and in addition a factor of 2. So now I keep gamma in the numerator, I divide everything by m. I already pulled out m omega squared, so what is left here is simply the difference in frequency squared plus, now see I pulled out a factor of 4, so overall I get gamma half squared. And so now we can plot the spectrum and indicate the different parameters. I get a Lorentzian peak here, and if you look at this, the full width at half maximum, how do I obtain the full width at half maximum? Well, I would demand that the value of the denominator is twice as large as at resonance. Resonance means I set this to 0. If it is supposed to be twice as large, then the difference in frequencies has to be equal to gamma half. So I have to move out by gamma half to one direction in order to reduce the peak down to half its value. And so the full width at half maximum is simply gamma. And so what is the height of the peak? Well, just insert little omega equals capital omega, that is we are at resonance, then you will find that all of this expression turns into 4 divided by gamma. So together with the 2 down here, I have 2 divided by gamma times kBt over m omega squared. And remember that kBt divided by m omega squared is nothing but the variance in thermal equilibrium, the variance of the coordinate. So let's discuss this. Dimension-wise, this makes a lot of sense. You have the variance divided by gamma, and that is the dimension of x squared divided by frequency. Yeah? And secondly, we already had discussed that the area should reproduce x squared. Now, at least there's a chance for this to happen, because if the width is gamma and the height is essentially 1 over gamma times the variance, then probably the area will be such that the gammas cancel and out comes the variance. But still, this is something we have to check, because it's an argument that is only true up to a factor of 2 or so. And of course, the whole noise spectrum is symmetric in frequency. So that is the noise spectrum of the damped harmonic oscillator that you would expect to observe in an experiment. In particular, you can read off the resonance frequency, you can read off the damping rate, and by looking at the area, you will be able to read off the temperature. Okay, so as a last item, let's just briefly check the area in order to check whether everything is correct. Okay, so let's calculate the integral over all frequencies of the noise spectrum. Now, I want to calculate this within the approximation of having this Lorentzian peak, because then it becomes simpler. And so in that case, I simply exploit the fact that I know the frequency spectrum is symmetric, so I would integrate over the Lorentzian peak sitting at minus the resonance frequency and the one at plus the resonance frequency. That just gives a factor of 2. So then I look at the spectrum which we had just derived previously. They can pull out the prefactor kBt divided by 2 times m omega squared. And so what remains is to evaluate this integral over all frequencies of gamma divided by frequency difference squared plus gamma half squared. So that's a typical Lorentzian integral. Let's do this. It's best, obviously, to rescale things such that I measure the frequency with respect to gamma half. So I want to have new variables. And if I want to do that, I can pull out a factor of gamma half squared from the denominator. And what I find is two over gamma in front, integral dy gamma over 1 plus 1. So the gamma cancels, and this integral over all y, 1 over 1 plus y squared is simply pi. So all of this integral just simply gives me 2 pi. The 2 pi cancels with the 2 pi down here, the 2 cancels with the 2 down here, and so overall what I find in the end is that I obtain kBt divided by m omega squared, and this is exactly the variance. So what this check really tells me, apart from having been able to calculate this integral correctly, is that the form or my application of the fluctuation dissipation theorem was correct. Because inserting the susceptibility, I obtain a noise spectrum that, when integrated over all frequencies, exactly reproduces the value of x squared that I expect automatically from the equipartition theorem. And so this is also worth a remark. If you apply the Boltzmann distribution to some classical system, then you would only calculate quantities like x squared, or maybe the average of x to the 8th power. That is, in particular, equal time quantities. And the idea is then the fluctuation dissipation theorem is somehow going beyond that, in that it also tells you about unequal time correlation function, about spectra. So this is a little bit more than just being able to calculate the distributions of all kinds of observables at a given time. Maybe it's amusing still to check the same thing for the quantum case, but we won't really carry out a full calculation, because if you look at the fluctuation dissipation theorem in the quantum case, it contains this factor, and we already said that for the quantum case, for the full quantum case at 0 temperature, this turns into 2h bar times the theta function in omega. Now if you compare this with the classical case, in the classical case at this point we had kBt divided by omega. So how do I turn this classical case into that case, apart from the theta function that is? Well, if I want to reproduce this from here, I simply would have to insert kBt becoming h bar omega, right? If I replace kBt by h bar omega, I will simply obtain this prefactor. So what happens now, if I calculate the integral over all frequencies in the quantum case, is the following. First of all, I would get only 1/2 of the overall contribution in the classical case, simply because the theta function cuts off the negative frequencies. And then I simply can take the formula that I already derived for the classical case, but I have to do the replacement. kBt goes into h bar omega. And the omega in question then would be the omega at resonance, capital omega. So what is this? Well, if I replace kBt by h bar omega, I have this factor of 1/2 in front. Overall, I get h bar divided by 2 m omega. Now, if you remember what we learned about the quantum mechanical harmonic oscillator, this is precisely the variance of x in the ground state. So again, this works out nicely. Okay, so this basically finished this discussion, and what I want to briefly mention now is what would really happen if I were to measure in an optomechanical system where instead of having a single harmonic oscillator, a single normal mode, I really have a collection of them. Okay, so what happens if I have many oscillators, but in particular many independent oscillators? Because all these mechanical normal modes are really independent. They have been chosen to be independent. So the situation in this case would be that the displacement which I measure is really a sum over these normal mode coordinates. And then depending on how you define them, they are possibly weighted by some factors that depend on the normal mode shape, on the shapes of the normal mode functions, the mechanical normal mode functions. So it might be that the signal that you measure is really such a weighted linear superposition. And so then, if you look at the spectrum, for example, or equivalently Fourier transform of the correlator, then what you would find is the following, that you simply have a sum over many independent contributions each of them weighted according to the squares of these values, and that's it. So the independence came into play because otherwise you would have cross terms here. You would have a double sum and you would have correlators xi, xj, but since these vanish, they drop out. And so what people really observe in the experiment then would be something like this. I only plot the positive frequencies because by now we already know that everything is symmetric. And so what you would have is a series of resonances at different frequencies with peaks that have different widths according to the different damping rates, because sometimes, according to the geometry, some of those mechanical resonances may couple more easily to the environment and others couple weakly. So it's something like this. And so, what do you extract? Once again, you extract the series of resonance frequencies. You can extract directly the damping rates. And then it depends a little bit whether you know your masses, in which case you can extract temperatures, or maybe you know the temperature, at least for the given initial temperature, and then you extract the masses of these oscillators. Okay, so this would be a typical spectrum, and then of course there are issues that we will discuss later, namely that there would be what people call a noise floor stemming from the imprecision noise of the experiment, that you are not really able to detect precisely x of t, but there will be extra noisy contributions down here. Okay, so are there any questions left? Well, if not, then thank you for today.